I said in the intro video, the key things to know about quadratics are how to recognize them, how to factor them, and how to distribute them. I will stand by that statement. Another thing worth knowing, though, is your special quadratics. But this is not anything new that you need to learn. All of your special quadratics, they can be derived using the same principles as any other quadratic. Really, your special quadratics are just quadratics that show up frequently enough on the GMAT that it is worth simply memorizing them and what they look like. And by doing that, it should actually save you time in the long run, because you won't have to manually factor or FOIL them when they show up. So what are our special quadratics? There are 3 of them. Remember, quadratics can be presented in 2 forms: their factored form or their distributed or FOILed form. So you want to be able to recognize them in either of those forms, and the same goes for your special quadratics. So I will present their factored form first. And so our first one is a plus b squared. And then we have a minus b all squared. Then our last one is our difference of squares, which is a plus b times a minus b. And we will see why this is called a difference of squared in a second. And so these are our factored forms. And to show you that your special quadratics are no different than any other type of quadratic, let's get our distributed form by FOILing these guys out, which after today, you shouldn't have to do. So a plus b squared, that would just be a plus b times a plus b. And so this would be a squared plus ab plus ba, which is the same as ab, plus a b squared. And so this is no difference than just saying x plus x, which is equal to 2x, except in this case, x happens to be equal to ab. So this is really just a squared plus 2ab plus b squared. What about a minus b squared? A minus b squared looks pretty similar to a plus b squared, except here we're going to have a squared minus ab minus ba. And then we got negative b times negative b, so that is going to be plus b squared. And so when simplified, this gives us a squared minus 2ab plus b squared. But the only difference here is our middle term. What about our difference of squares? A plus b times a minus b. So this would be a squared minus ab, and here we would have plus ba. And then b times negative b is going to be minus b squared. So here, with a difference of squares, our middle term cancels out because we have minus ab plus ab, which gives us 0. So we are left with just our 2 end terms, a squared minus b squared. So here, you should be able to see why this is called a difference of squares. All of the time, when this shows up, I ask people what this is called, and they say, oh, I recognize it, but I don't remember the name. There is no reason to not remember the name, because the name describes exactly what it is. You have 2 squares, and you are taking the difference of them. So difference of squares is very useful we will dedicate a whole video just the difference of squares. So let's give an example for each of these guys. So for a plus b squared, that might be something like x plus 3 all squared. And so this would be in its distributed form x squared plus 2 times 3x. So that would be 6x plus 3 squared, which is 9. For a minus b squared, let's maybe show a way they like to get fancy and sort of disguise these sometimes, because that's the real reason you want to memorize these guys, is so not when they present them in their straightforward way, when they present them in a bit of a disguised manner. So you might have something like square root of x plus the square root of y. Okay. Be a minus sign. Minus square root of y squared. And so what would this be? And so in this case, our a squared would be square root of x times square root of x, which is just x. So this would be x minus 2 times the square root of xy plus y. So if they were to give it to you in this format here, for example, you would have to recognize that this is a special quadratic and probably put it in this format here. What about a difference of squares? So this would be something like x squared minus 36. And that would be equal to x plus 6 times x minus 6. So those are your special quadratics, every single one of them worth knowing. Let's do a problem now, testing what we learned. What is the value of 5 raised to the x plus y squared over 5 raised to the x minus y squared? So one thing I think I said earlier was usually with quadratics, if they give you the factored form of a quadratic equation, it probably means you have to put it in its distributed form. And if they give you the distributed form, it probably means you got to put it in its factored form. So we'll do that here. Before we do that, we can say, well, this is sort of an exponent problem as well. So we are dividing exponents with the same base. We can think of this as just being 5 raised to the a over 5 raised to the b. That should be equal to 5 raised to the a minus b, except in this case, a happens to be equal to x plus y squared, and b is equal to x minus y squared. So that would give us 5 all raised to the, and now if we were to distribute these out, it would be x squared plus 2xy plus y squared minus, and then here's where you got to be a little bit organized because it's going to be minus this whole thing distributed out. So we got to put it in parentheses, x squared minus 2xy. Plus y squared. So when we start simplifying this, it would be x squared plus 2xy plus y squared minus, so it would be minus x squared plus 2xy, right? Because we have a negative times a negative. So plus 2xy, then minus y squared. We have to remember also, this is our question, right? And so I always like to put little question marks so I remember. I'm rephrasing my question here. This isn't information that I was given. So let's start combining terms, and we have 5 raised to the, looks like our x squareds cancel out. Looks like our y squareds cancel out. And we're just left with 2xy plus 2xy, which is 4xy. So this whole thing is just asking us, what is 5 raised to the 4xy? And then we can go even further, I think, because this is a data sufficiency question. And so if I'm looking for 5 raised to the 4xy, well, really, I just need 4xy. And so this 5 doesn't matter. This isn't even really an exponent question anymore. They're just asking me, what is 4xy? And really, if I need to find 4xy, all I really need to find, if I want to put it in its simplest form possible, I want to extract the maximum information I can from my prompt. this whole question is really just asking me, what is x, y? So it's not even really a quadratic question anymore. We were able to use our knowledge of quadratics to turn it into a much simpler question. So we're just looking for x, y. Statement 1 says x squared plus y squared is equal to 13. So does this help me get x, y at all? Is there anything I can do with this? It sort of looks like it might be a special quadratic, but if you go back and look at our list, I don't think there was anything on it that looked like this. There's no such thing, as far as I know, as an addition of squares. So I don't think we can do anything with this, and we cannot get x, y. At least we cannot get a single value for x, y, and so this is going to be insufficient. And what about statement 2? Because we did our work up front, we don't really have to do anything with this guy because it directly answers our question. That's sort of the dream scenario with data sufficiency. Do your work up front, slow down to go faster later on. So xy is equal to 6. That directly answers my question. I no longer care about this whole guy because I rephrased my question, and the answer is B. So let's take a look now at difference of squares in the next video.